Good morning, class. What I thought I'd do with this video was to go over the answers to the quiz 7 and also to the final examination. I should be, I think, mailing your tests to you as soon as I'm sure I've got everybody's tests turned in. So first of all, let's look at the quiz 7. We have 100 grams of barium fluoride dissolved in water. Once equilibrium is reached, the concentration of barium is this moles per liter, and fluorine is this. Write a chemical equation for the dissolution into its ions, write the expression for the solubility constant, and then using the concentrations, calculate the solubility constant. Okay, so first of all, barium fluoride. There's a little A in there. Here, let's barium fluoride decomposes to form barium ion and 2 fluoride ions. So that's the answer to the first part. The solubility constant and the solubility factor is going to equal the concentration of barium times the concentration of fluorine squared. Now from here we get that the concentration of barium is 0.1817, and fluorine is 0.0363. So this is 0.01817, and this is 0.0363. Make sure I got that right. Yeah, okay. And this will be squared. And so if we do the multiplication here, 239 times 10 to the minus 5. So this is one answer, this is another answer, and this is the first answer. Okay, the second question says the solubility constant of lead, given the formula here, is 1.2 times 10 to the minus 15. If this amount is dissolved in water, what is the concentration of lead and the hydroxide ion? So we have lead hydroxide decomposes to form lead ions plus hydroxide ions, 2 of these. And this is going to be X and this is going to be 2X. And you know that 1.2 times 10 to the minus 15 is equal to the concentration of lead times the concentration of hydroxide squared. Now technically over here we'd have to calculate some concentration and subtract X from that. But because this number is so small, we can assume that the amount of lead hydroxide that is removed is inconsequential. And so we can use this information. We put X here and 2X here, and that's squared. And so this is going to equal to 4X cubed is equal to 1.2 times 10 to the minus 15. And so X cubed is going to equal to 3 times 10 to the minus 16. That's dividing both sides by 4. So it's going to be times 10 to the minus 6, and whatever the cube root of 300 is, I'd say it's something like 8 times 8, 64 times 8's 4 something. So it's going to be about 6 and change. I don't have my calculator with me, so but your answer is going to be the cube root of this number right here. Now the second part of this, we're given that the hydroxide ion concentration is 0.1. And we're asked what the lead concentration is. So what we do this time is we say that 1.2 times 10 to the minus 15 is equal to the lead concentration, which we don't know, which we can also call X if you want to, times 0.1 squared. 0.1 squared is 0.01. You divide both sides by that, you get 1.2 times 10 to the minus 13, and that's going to be the lead concentration. And so those are the two problems on the quiz, and that represents the answers to the quiz. Now let's move on to the final examination. The first question here wants us to find the boiling point of a solution that has 92.1 grams of iodine and 800 grams of chloroform. And the boiling point of chloroform is 61.2. The freezing point is minus 63.5. And the boiling point constant is 3.62, and the freezing point constant is 4.68. So let's look at this. First of all, we have to calculate the number of moles of iodine we have. I2 is going to equal, the molecular weight is 2 times the gram atomic weight of iodine, which is 126.9, so that's 254.8 grams per mole. And we have 92.1 grams of that, and so if we divide that by 3.8, this is a 3, and the answer here is going to be 0.363 moles of iodine. Now the molality is equal to moles divided by kilograms of solvent. In this case, it's 0.363, and we have 800 grams of solvent, which is 0.8 kilograms of solvent. And so that's going to be 0.454 molal, however you want to say it. This is a 4. So now the boiling point, the new boiling point, is going to equal the old boiling point of the pure substance plus the molality times the boiling point constant. And then the freezing point is going to equal the old freezing point minus, because it depresses the freezing point, times the freezing point constant. So in this case, it's 61.2 plus 3.62 times 0.454. And in this side, it's going to be minus 63.5. And remember, when you add stuff, it depresses the freezing point, so it's minus 4.68 times 0.454. And so this is going to equal 62.8 degrees centigrade, and this is going to equal minus 65.6 degrees centigrade. Now, a common mistake here that people made was they added this instead of subtracting it. You subtract it in this situation. So that's number 1. Number 2. Number 2 states that we have the Kc for this reaction is 82, and here's the reaction. And we have 0.83 moles in 10 liters of solution. So what that means is that the molarity of both of these is these numbers divided by 10. Okay? And so one mistake that was made is people forgot to divide by 10. So first of all, you have I2 plus Cl2 is equal to ICl, and the K equilibrium constant is going to equal the concentration of ICl squared divided by I2 times Cl2. So if we make our little table, and this is initial, change, and final or end, we know that I concentration is 0.083. That's 0.083 divided by 10. This is 0.083, and this is 0. The change is minus x, and plus 2x. And then the final is 2x, 0.083 minus x, and 0.083 minus x. So if we put this over here, 82, which was is equal to 2x squared divided by 0.083 minus x, and it's going to be times the same thing, so we'll just say squared. And now if we do the math here, we get 0.006889, that's this squared, minus 0.166x, that's 2 times this, plus x squared, and then it's going to equal 82x squared. Well, it's going to equal, I'm sorry, if you divide this, wait, let me do this over again, sorry. This is in the denominator, and on top we're going to have 4x squared, and then this is going to equal 82. So we multiply 82 here. We actually take this over to this side of the equation, and we get 82x squared minus 13.61x plus 0.565 is equal to 4x squared. We subtract x squared from both sides, and that just changes. If we can just change that to 0, and now this becomes 78x squared. So now this is your quadratic equation. You put this in to the quadratic formula, and you can either do it by hand. Remember, it's negative b plus or minus the square root. It's negative b plus or minus the square root of b squared minus 4ac over 2a. But I told you that you could use a quadratic formula calculator, which you can get online. And if you do that, you get two answers. One is 0.1065, and the other one is 0.068. And this number is greater than the number you started with, so it can't be right. So this is the right answer right here for x. And if we put that in for x, that means the concentration of ICl, which is 2 times that, is 0.136 molar. The concentration for Cl is going to be the 0.083 minus this number here, or 0.015 molar. And then the concentration for I is also 0.015. And so that's how you do this problem. Okay, let's move on to number 3. And number 3 is a lesson in Le Chatelier's principle. And the questions are, does the amount of acetone, and the formula for acetone is right here. So it's this stuff right here. So it's one of the products. Does acetone increase, decrease, or remain the same with each of the following changes? If you increase the temperature, this is an endothermic reaction, which means you have to add heat on the reactant side. If you increase the temperature, it's like adding heat or adding to a reactant, which drives the reaction this way. So the answer to the first one is increase. If the pressure is decreased, it favors the side with less gas, which is this side over here. So it decreases the amount. It favors the side with the less gas, which is this side right here. And so it would drive the reaction to the left, so it decreases the amount of acetone. C, if argon is added, argon would have the same effect in a closed container as increasing the pressure. Increasing the pressure will, the second one, if you decrease it, it'll go to the side with more molecules. I got that backwards. That's wrong. So the answer to number 2 is increase. So the first one is increase. The second one is increase. If you add argon, it's the same as adding more pressure. So you're increasing the pressure and driving it this way. So it'll decrease the amount of acetone. If hydrogen is added, it will decrease the amount of this because it drives the reaction in this direction. Catalysts that added will do nothing. Acetone is removed. That would tend to drive more acetone being produced, but you're removing it. So I will accept any answer here. Increase, decrease, or remains the same, because it all depends on how much you take out. And then lastly, the volume is decreased. If the volume is decreased, the pressure is increased, so it has the same effect as increasing the pressure, so it will drive the reaction to the left and decrease the acetone. For some reason, I made the mistake of putting the same question that was on the quiz, which I previously did. So this was an easy 10 points for everybody that noticed that. So let's go on to number 5. I don't make that mistake often, but I did this time. Okay, so using Appendix G, calculate delta S, delta H, and delta G. All right, so the first thing I did was for each of these, I wrote down the heat of formation. Oops, let's get over here. So we have 2HCl gas plus lead solid goes to form lead chloride solid plus hydrogen gas. So first you have to have the heat of formation, the enthalpy of formation, and the free energy of formation for each of these. And this is what you get from the back of the book, from the index, or from the Appendix G. And looking these up, first you can write these in because these are elements. So you can write zeros for the delta GF and the delta HF for elements, not the S though, because even elements have some degree of entropy. But this is minus 92.307. This is 186.9. This is minus 95.299. For lead, it's 64.81. Over here, this is minus 359.4. This is 136.0. This is minus 314.1. And this last one here is 130.7. So the delta H is equal to the sum of the products minus the sum of the reactants is equal to the products here is lead chloride, so it's minus 359.4, and that's the products, minus, remember you have to take 2 times any of these numbers, so this is 2 times 92.307, 0.307, and this is a minus number here. And don't lose your signs because that's important. And if you do the math here, you get minus 174.6. For delta S, the formula is the same. So you'd start out with 136.0 plus 130.7, that's the two products, minus the two reactants, and again you have to take 2 times 186.9 plus 64.81. And again, if you do the math here, you get minus 171.91. Now, this is joules per mole degree centigrade. This is kilojoules per mole. And there's a reason I keep track of that, and you'll see in just a second. Delta G is going to be, again, the products, which is minus 314.1. Minus, again, 2 times a negative 95.299. You do the math here and you get negative 123.5 kilojoules per mole. And I said to do by an alternate method. Well, the alternate method is to say that delta G is equal to delta H minus T delta S, so that we'll leave delta G blank and see what we get. So that's going to equal delta H, which is minus 174.6 minus 298 for the temperature. It has to be in Kelvin. And delta S, remember this is joules, so we have to move this way over here. So this is minus 0.17191. And if you do this math, you get negative 123.5. So that's number 5. Number 6, a solution containing 30 grams of a protein in 1 liter at 25 degrees has a measured osmotic pressure of 9.4 millimeters. What is the estimated molecular weight of the protein? All right, in order to do this, we have to first know the formula for this. Is the osmotic pressure is equal to the gas constant times the molarity times the temperature in Kelvin. And so we know that the osmotic pressure is 9.4 millimeters. Now, because we're going to use an R, which is 0.0821, the pressure has to be changed to atmospheres. In order to do that, you take 9.4 divided by 760 millimeters in an atmosphere, and that gives you a number 0.0124 atmospheres. Now, we also know the temperature is 298 degrees Kelvin. If we rearrange this, molarity is equal to the osmotic pressure divided by RT. So this is going to be 0.0124 divided by 0.0821 times 298. So the molarity of this has to be 5.05 times 10 to the minus 4. So that's the molarity. Now that's moles per liter, And we know that we have 30 grams in a liter. So if we take that 30 grams per liter and multiply that by liters over 5.05 times 10 to the minus 4 moles, then these liters cancel out, and we divide this into 30, and we get 5.94 times 10 to the 4 grams per mole. So the molecular weight is about 59,400. Okay, the last problem says that at 0 degrees in 1 atmosphere, 7/10 of oxygen will dissolve in 1 liter of water. How many grams of oxygen will dissolve in 1 liter of water if the pressure is increased to 3 atmospheres? This is Henry's law, and Henry's law states that the concentration in grams is equal to a constant times the pressure. And so if we know that we have 7 grams per liter is equal to the constant times 1, then the constant is going to be equal to 0.7 grams per liter. So that's the constant. So now we change the pressure to 3, and we want to know the new concentration. We know that 0.7 is the old times 3. So now the concentration is going to be equal to 2.1 grams. So that's the answer.